Hello, welcome to the channel of Nammagiri Academy. This is the next lecture in the series of multiple integration, and in this lecture we shall see the uh, change of variables in uh, double integration. So let us recall how we change variable um, in the integration of one variables. So I have already mentioned in the beginning of this series of lectures that I am assuming the knowledge of the integration of one variable. So when we have something like this, integrating when we are integrating a function um, of x, suppose if we encounter something like this, and then sometimes we may be required, or it is desired, or it is convenient to express x as a function of some other variable, let's say u, uh, and in that case also we have to uh, replace this differential by uh, and therefore, and also if we have the limits of integration over here, something like a b, then we have to correspondingly change the limits of the integration, and our integral becomes f of g of u g prime u du. Now we have this f of g of u is a function in u, and this is, so f of g of u multiplied by g prime of u is a function in u, in fact, and now this is the function that we shall integrate with respect to u. And when x takes value a, we find out what value u takes, and that is suppose x, suppose this is u1, then u1 is g inverse of a, and this is g inverse of b, assuming that everything is fine. So there are certain we have to exercise some care while taking these inverses, but with this, this is the procedure or the formula for the change of variables in one dimension, or other integration in one variable. Now we have something similar in case of two variables. Suppose we are trying to integrate a function in two variables, a real valued function. Okay, so something like this. So I shall write this as d dy dx or dx dy, whichever, depending on the case. So this is an iterative integral. So this inner integral will have limits of integration between which y varies, and then outer integral will have the limits for x. Now what we do is, for change of variables, now as we did here in case of one variable, we expressed x as a function of u. So if you want an example, remember this one. In case of one variable, often we do this integral of 1 over um, x square dx. So here I will write. Here we substitute just to give you an example, to so that you recall. X is equal to tan u is the standard substitution, and then dx equal to secant square u, which is the derivative of tan u. So here x is g of u, then dx is g prime of u. So here x is tan u, so now dx is derivative of tan u, that is g prime of u multiplied by du. And now if we substitute here, this dx now becomes secant square u du, and x is tan of u, 1 plus tan square of u, which is now secant square u du divided by secant square u du, the integral, the integral. So this is integral du, which is u, but u is tan inverse of x. So this is tan inverse of x, and that's how we come to the conclusion that integral of dx over 1 plus x square is tan inverse of x. So that is by substituting x as a function of u. So we want to do something similar here in case of two variables now, but here we have some more difficulty. It is not as simple as this. Here we have two variables x and y, and therefore we shall have to replace them with two new variables, let's say u and v. Okay, so now integration by substitution, what do we do? What is the general method? So we first, as here, as we expressed x as a function of x as a function of u, here we again we shall express this x as a function of u and v. So and we shall call this function again as x, okay, and also y as a function of u and v. So we are defining two new variables u and v, and x depends on uv and y also depends on uv, and those functions we can call them as g and h if we want, but we don't want to unnecessarily insert or unnecessarily introduce new variables, so we shall just call those functions also by x. Now this integral now will be f of this, now x and y will be now x of uv, y of uv, and also this dy dx will should convert into dv du. But is that all? Was that all here? Here in case of one variable integration, we also had this term of g prime of u. This is uh, the the so-called change of variable formula. This is the essence of change of variable, in fact. So what should we what is the analogous uh, the thing I mean to is double integration? It is called as Jacobian. Okay, so I will here write J for Jacobian. We multiply this by Jacobian and then we write dv du. So what is this Jacobian and how to compute it? And again here we have double integral, and so when we are converting this x and y into u and v, we shall also have to take care of the limits of integration, because now we don't have x and y varying between the given limits. We have u and v varying between their respective limits. So we shall have to see between which numbers u and v are varying, as x and y are varying between their given limits. So that is this something that we shall see later, but let us see what is Jacobian is, that we must multiply this function by before we can actually compute this double integral. So this Jacobian is defined as this. It is the determinant of this matrix, which is given in terms of partial derivatives. Now remember that earlier here we had g prime of u, the derivative of g with respect to u. Now here, since we have functions of several variable, we don't have we have partial derivatives. So the job will be done by partial derivatives, and we shall have some expression in terms of partial derivatives. Alright, so Jacobian is given as the determinant of del x del u del y del u del x del v del y del v. So you can also write this as del x del u del y del v minus del x del v del y del u. Remember that this will be a function in u and v, because x and y are functions in u and v, and we are differentiating them with respect to u and v. So we shall get expressions in u and v, functions in u and v again. So each of these, del x over del u, del y over del v, del x over del v, del y over del u, each of these is a function in u and v. So this Jacobian will be a function in u and v. So now this we have a function f. X will be replaced by an expression in u and v, y will be replaced by an expression in u and v, because y is now expressed in terms of u and v. J will be a function in u and v. So therefore this whole term will be a function in u and v, and now we are integrating that function with respect to u and v, or v and u, as the case is. And this double integral or the iterated integral will have corresponding limits. We shall have to compute those limits. So let us take one example. An example will make it clearer. So compute double integral of e to the power y minus x divided by y plus x. So why do we do this? This is because substitution or change of variables You can call it substitution, or you can also call it change of variables, because as you can see here, we are changing the variables from xy to uv. So this substitution or this change of variables makes things easier. Hmm? dy dx over region R, where R is the region bounded by the lines y minus x equal to -1, y minus x equal to +1, y plus x equal to +1, y plus x equal to -1. So these are the four lines between which R is bounded, and we have to integrate this function in this region. So let us draw the region, and let us also see what is sorry. Okay, so x plus y plus 1 is this line. This is 1 on the x-axis, this is 1 on the y-axis. X plus y minus 1 is this line. X plus y minus x equal to -1 is this line. Which passes through these 2 points exactly, and y minus x equal to +1 is this line. So it is this diamond shape that is R, and we have to integrate this function over R. Now you see that this function is not so easy to integrate, whether you integrate it with respect to y first or with respect to x first. It is not impossible, but certainly not easy to do that. So here we may think of changing the variables. So let us substitute so this substitution of variables and changing the variables is something that you will develop this intuition of when to substitute and when to change the variables only by practice. When you solve several variables, you will gradually develop this sense of when to substitute and what to substitute for what, as in case of one variable integration. We have seen when we studied one variable integration, we solved several examples and then we developed that intuition. So also in this case, it is only by practice that we gradually start sensing when to substitute for what. Okay, substitute. Let's say So here y minus x, so we want to write x and y both as functions of new variables u and v. And here it is now convenient for me to first express u and v as functions of y, because here y minus x and y plus x are something that are creating a little bit of trouble for me here. Okay, so therefore if suppose y minus x is just one term rather than it's difference of two terms, then it will be very easy for me. So I will replace this y minus x by one variable u, and similarly the sum of these two variables y plus x also should be replaced by one variable, that and that is called that as v. Okay, so now here observe that here we have expressed u and v as functions of x and y rather than expressing x and y as functions of u and v, which we desire to do. But that's not a big problem. We can always sort of solve these and convert rather find out what x is in terms of u and v, and similarly what y is in terms of u and v. So let us add these two equations. That will give us, that will actually after adding these two will annihilate x. We shall get 2 times y equal to u plus v. So y equal to, this gives y equal to u plus v over 2. And if we subtract this first equation from the second, y annihilates and we get 2 times x equal to v minus u. So that gives us x equal to v minus u divided by 2. Okay. Now what are the limits of integration? So let us first write this. We are what is our function here? E to the power y minus x over y plus x. So y minus x is u, so we can write this as e to the power u over v. Okay, we can write here du dv or dv du, whatever. We are yet to find out the Jacobian, which we shall do very soon. But also we have to find out the limits of integration. Now observe that v, what are the limits of integration of v? V is y plus x, and y plus x, the region is bound between y plus x equal to minus 1 and y plus x equal to plus 1. So it is between these two parallel lines. So that means v varies from -1 to +1. Similarly u is y minus x, and y minus x varies from -1 to +1. This is the region between which y minus x varies. So u varies from -1 to +2. So we have also determined the limits of integration. All that remains to be determined now is the Jacobian. What is the Jacobian? Jacobian del x over del u del y over del u del x over del v del y over del v. This determinant needs to be computed now. Okay, now we have expressed x as a function of u. So this is v minus u over 2. When we differentiate this with respect to u, what we get is -1 over 2. Okay, del y over del u, that is +1 over 2. Del x over del v is +1 over 2, and del y over del v is +1 over 2. Okay, so what is it? This is -1 over 4 minus 1 over 4, which is -1 over 2. Okay, so this Jacobian is denoted by del x comma y divided by del u v. Remember this. You can use this symbol. You should use this. Earlier I did not use. I just wrote J for Jacobian here, but technically we use this symbol for Jacobian for two variables. Okay, so what is it? Let us compute. E to the power u over v -1 over 2 dv du. Now here observe that the limits of integration of v are constants, two constants, and similarly that of u also are two constants. So it's a rectangular region in the uv plane. When we look at it as a region of integration in the new variable system, new coordinate system, uv coordinate system, it's a rectangle wherein suppose this was xy coordinate system, this was y-axis. If this is now uv coordinate system, then it is v is varying from -1 to +1, and u is also varying from -1 to +1. So it is actually a square. So this uh, region has got transformed into this new region in the new coordinate system. Okay, fine. So now you can take this negative 1 over to outside. Alright, now what should we do? um, Fine. So this is negative 1 to 1 and integral this. I think now it is not very difficult because e to the power uh, u. Now since we shall be um, difference or integrating with respect to v first, should be treated as a constant. So we can write this as um, uh, u over v. Maybe we should change the let us change the order over here rather than um, struggling with this. What I will do here is first, now since we are integrating over a rectangular region, we can change the order. So first we can integrate with respect to u and then with respect to v, because that will at least postpone the possible difficulty. Here I am facing the difficulty of integrating with respect to v first. Now since u is in the numerator, we can relatively easily integrate with respect to u. It is like e to the power constant multiplied by u, so where constant is 1 over v. So the integral will be e to the power u over v divided by 1 over v. This is the integral, and this is the integration is over, so we shall write it in this way, negative 1 to 1. These are the limits of integration. And so here again we see the power of changing the order of the integration. It hasn't solved our problem as yet, but at least it has helped us to go one step ahead. Earlier, for a moment I was faced with the problem of integrating e to the power u over v with respect to v, but if not with respect to v, we can at least integrate with respect to u and come to this conclusion, and now see whether we can integrate with respect to v. Alright, so this is v e to the power u over v dv. So I'm sorry, we need to okay, dv. All right, so now we shall have to substitute for u. So negative 1 over 2 integral negative 1 to 1 v e to the power 1 over v minus v e to the power minus 1 over v dv. I think even this is not easy to integrate. Integral of v e to the power 1 over v dv and integral of v e to the power negative 1 over v dv is something that at least I am not sure how to integrate. But okay, you can try to integrate it, or maybe it may not have a closed form. And I think integral of e to the power 1 over x, or any variable x or v or whatever, does not have a closed formula. So anyway, but here in this case the objective of this problem was not to actually integrate and compute the integral. It was just to show you how to change variables, how to implement the change of variable formula, so which we have done successfully. So therefore fine, we shall leave this example over here. Alright, and we shall proceed further. Now this change of variables formula has a very specific use, or it comes to our use in a very specific situation where the region that we are trying to integrate has a circular shape, or maybe semicircular or quarter circular shape. So in that case we make a very specific substitution, which is called the change into the polar coordinates. Changing into polar coordinates. In such cases, as we have seen that x is a function x of variables u v is a function y is a function of the same variables u v. Okay, now what we do here is that we express x as function of r and theta, where r is the length. So if x comma y is a point over in this plane, then r is the length of the segment that connects origin with xy, and theta is the angle made by this arm with the positive x-axis. So these two are again real numbers, and we sometimes convert. So for every xy we can express this point by unique you can say unique pair r comma theta, as long as we restrict the value of theta between 0 and 2 pi. Okay, so therefore we can and this new coordinate system in which we express every xy in terms of r theta is called polar coordinate system. So here in polar coordinate system, instead of some random u and v, we particularly stick to r comma theta. All right. So now, um, when we are uh, using these polar coordinates, what is the function for what is the expression for x that we use in terms of r and theta? It is r cos theta, and for y we substitute r sin theta. So because if you look at this, if this is r and this is theta, then this three segments, if we drop a perpendicular from point xy onto the positive x-axis, then that gives us a right angled triangle, and this is the x coordinate, that is this length is equal to the x coordinate of this point, and this x is nothing but r multiplied by cos of theta, because cos of theta is the adjacent side of this angle theta, that is x, divided by the hypotenuse, that is r. So cos of theta in this case is x over r, and sine of theta in this case, this is theta, which is opposite side, and this length of this opposite side is y, that is the coordinate of this point, so that is y over r. So x is r cos theta and y is r sin theta according to this diagram. So therefore x coordinate becomes r cos theta and y coordinate becomes r times sin theta. And if we make this substitution, then the Jacobian in this case becomes see, this is a very specific substitution. Now we are not making in some general substitute here. In the previous problem we substituted x equal to some, I think, v minus u over 2 and y equal to v plus u over 2, and this substitution may differ from problem to problem depending upon which function we are trying to integrate and what our region of integration is. But when the region of integration is circular or semicircular or something that has something to do with a circle or a disc, then this kind of change of variables comes in very handy. This change of variables. Alright, so now this is, what is this determinant of first partial derivative of x with respect to r, del x over del r, del y over del r, del x over del theta, del y over del theta. This is del x over del r is cos of theta, del y over del r is sin theta, del x over del theta is negative r sin theta, and del y over del theta is r cos theta. It's so r cos square theta plus r sin square theta. If we factor out r, then inside the bracket we get cos square theta plus sin square theta, that is r. So Jacobian is r. So Very simple. So now we have computed the Jacobian equal to r. So whenever we are going to use polar coordinates for integration, now we shall not have to compute Jacobian over and over again. We know it's r. So we can simply substitute the Jacobian equal to r. Suppose now let's take one example. Compute integral of sine of x square plus y square dy dx over region R, where R is a semi-circular disk with center at the origin and radius equal to 1. Okay, so standard circular, something like this. So if we draw the diagram, then the disk is like this in the upper half plane. Alright, so okay, so not a very good diagram, but please understand that this is a semicircular disk. This is 1 comma 0, this is 0 comma 1, and this is negative 1 comma 0. Alright, so alright, so let us substitute here now. Since we are dealing with the semicircular disk, it is our first instinct is to convert this integral, rather convert these variables into polar coordinates. Okay, and also observe here that the expression, this expression is x square plus y square, and whenever we have an expression of this sort, it is this always rings a bell, and it tells us that possibly it will be a good idea to change the coordinates into polar coordinates, because we substitute r cos theta for x and r sin theta for y, and when we do that, we shall get the sum r square cos square theta plus r square sin square theta, and cos square theta and sin square theta will add up to 1 after factoring out r square, and that will simplify the expression just to r square. Alright, so that is so here the region as well as the function both are pointing toward the change of coordinates to polar coordinates. Alright, so let us substitute x equal to r cos theta, y equal to r sin theta. Now what is important over here is to decide the limits of integration. here r varies, so theta is varying from 0 to pi, and for every theta r is varying from 0 to 1. All right. So r for let's say theta is varying from 0 to pi, and for every theta r is varying from 0 to 1. Okay, fine. And now what is the function? It is sine of x square plus y square, so that is r square cos square theta plus r square sine square theta. Now we have to multiply it by the Jacobian, but we know that when we use polar coordinates, the Jacobian is r multiplied by, here first we are integrating with respect to r, so dr d theta. Again here it won't matter whether we integrate first with respect to r or with respect to theta, because as you can see over here the limits of integration are both constant. So actually if we look at this region of integration in r theta coordinate system, this is r, this is theta, it is actually again a rectangular coordinate system. So r varies from 0 to 1, this is 1, and theta is from 0 to pi. So it is actually this rectangle that we are integrating over. Alright, but just make sure that you match these limits properly with r and theta. The limits of r are 0 to 1 and limits of theta are 0 to pi. So if you want to first integrate with respect to theta, then no matter, you can take this integral inside 0 to pi and first integrate with respect to theta and then integrate with respect to r. Alright, now we have chosen to integrate with respect to r first, so we shall do that. 0 to pi, 0 to 1, sine of, this is r square, r dr d theta. All right. Okay, so now we shall have to probably to integrate this inner integral, we shall have to use substitution. Let r square be equal to u. This is now the substitution in one variable, so therefore this is our usual method. So 2r dr, derivative of r square, 2r dr is equal to du. Therefore r dr, which is the term over here, is du over 2. So and limits of integration also will vary, as it I mean vary mean, let's see whether they vary. As r varies from 0 to 1, okay, r square also varies from 0 to 1, so u also varies from 0 to 1. So the limit actually will not vary. Sine of u, r dr is du over 2 d theta. Okay, this 1 over 2 can be taken completely outside, and this sine u du integrates to negative of cos of u. So this is 0 to pi negative cos of u 0 to 1 d theta. This is equal to um, 1 over 2 I will write this as this is 1 minus cos of 1, where 1 is in radians, okay, d theta. But in this can be treated as a constant, 1 minus cos of 1, and therefore it can be taken outside, and then we integrate d theta with respect, we integrate d theta and from 0 to pi, so it is integral, it becomes theta, and the limits of integration are 0 to pi, so it will be pi minus 0, so it is pi, so pi over 2 1 minus cos of 1. That seems to be the final answer. Now observe that this integral was not easy to compute over semicircular region if we tried to do it with respect to x and y, but when we changed that to polar coordinates, it became much easier. It became just sort of a cakewalk. So this is the power of change of variables. If we can do it properly, if we can properly make substitutions. All right. So that finishes our discussion on the change of variables. In the next lecture, we shall probably go over to triple integration. All right. So bye until then.